So my dear friends, question number 6. B is greater than or equal to 2, be a positive integer. Anu has an infinite collection of notes with exactly B minus 1 copies of a note worth B to the power k minus 1 rupees. For every integer k is greater than or equal to 1. Technically speaking, even this statement in itself has to be understood thoroughly before you proceed. What they actually want to tell you is, say for example B is equal to 2, that means Anu has, understand the question, infinite collection of notes with exactly one note of denomination. This will basically probably give you a better idea. B to the power k minus 1. So B to the power k minus 1, if B is 2, so that means 1, if B is 4, it is 3, if B is 3, it is 7, if it is, and likewise. Try to understand. When k is 1, 2 minus 1, so Anu has one note of 1 rupee, B square minus 1, that is 2 to the power k minus 1, 2 to the power 3, and this. The number of denominations are infinite, but the count of a particular denomination is limited to B minus 1 copies. That's what they mean to say. I'll give you another one also. If B was 3, Anu has 2 notes of denominations. Now, it would be 3 to the power k minus 1, 2, then 3, 8, 26, 80, and so on. So, for a given particular B, Anu has unlimited number of notes, but limited number of copies of a particular denomination, and denomination are not usual what it happens 1, 2, 3, n. It is basically of this denomination. The question becomes even more interesting henceforth. A positive integer n is called payable if Anu can pay n square plus 1 rupees by using some of these notes in the collection to someone, and they say if there is one such payable number, prove that there are infinitely payable numbers. They haven't said that show me which number is payable. They haven't said that show me all such payable numbers. They only said if there is one such payable number, show that there are infinite payable numbers. So this again is to a great extent inductive logic. Let us assume lambda square plus 1 is payable. N is equal to lambda. Let me say for some lambda, the amount lambda square plus 1 is payable in this denomination. What would this mean? This would simply mean that lambda square plus 1 is a summation of these currencies. So I would say B to the power k minus 1 and mk. K is taking values from 1 to infinity, but your mk is not open, it is 0, try to understand. First example, for B is equal to 2, with these currencies, say for a particular lambda 100, that means lambda is 10. So Anu has to pay somebody 101 rupees using this. May be possible, may not be possible, using these denominations. The question is not whether possible or not. The question is, if possible once, then is possible for infinite such payments which are of the form lambda square plus 1. So I assume that if it is possible once, let me say this holds true, Why I have taken mi to mk to be 0? Because I may not use a particular denomination. 2, 8, 26, 80, I would not use a 26 rupee note, I will not use a 80 rupee note, I will use 2 rupee, 8 rupee notes. But remember, if B is 3, then you have at max 2 such notes possible. Now, I am least concerned whether it is possible once for particular value, because it's not induction. They say if possible once, then up to infinite times. Now, all you need to do is, let me say mu is equal to some number related to lambda and b, and you show that mu square plus 1 is available infinite times for different values of b. So, for this you may have various options. You can write lambda b, but lambda b comes with a challenge when you write about mu square plus 1. So, this becomes lambda square b square plus 1. Now, this can be written as lambda square b square plus b square minus b square plus 1. So, lambda square plus 1 times b square minus b square minus 1. The challenge here is minus. Lambda square plus 1 is payable, so somebody can pay. But when it comes to b square, fair enough, lambda square plus 1 is payable and b is in your control. B square minus 1 is payable because that denomination note is with you, because b is already there. But the challenge is, how would you explain paying with a minus sign in terms of taking away money? Another option, although it's not impossible, but another option I would say was substitute mu is equal to lambda square plus lambda plus 1 times b. Now, mu square plus 1 would be lambda square plus lambda plus 1 whole square times b square. If you look at lambda square plus lambda, I will take lambda square plus 1 as one club and lambda the other one. So, this becomes b square times lambda square plus 1 whole square plus 2 lambda times lambda square plus 1 plus lambda square. I hope this is done, and of course a plus 1 again, right? It is mu square plus 1. So, mu square is this value and another plus 1 here. And when you realize, this basically is not that difficult to digest, that I can take out lambda square plus 1 from that value and proceed and then show that b square times lambda square plus 1 whole square plus 2 lambda b times lambda square plus 1 plus b square lambda square plus 1. Once again, a plus b square and a minus b square, because you have to write mu square plus 1. So, yeah, we have done correctly. This last term remains as a small thing to establish, plus b square minus, because everything else is done. It's easy to understand. Now, for that particular aspect, you again will have to create cases and show that in all possibilities, I repeat, that in all possibilities we get different values of it. The challenge here is that the number of notes are restricted. So, if I take a mu which is too big as compared to lambda, then I have to establish the fact that within those number limitations of copies of notes it is possible, or else we are done. All you can do better is justify this thing and you are done, because you keep on changing the value of b and you get infinite solutions. Ideally, what it was expected is that you show that there are different possible combinations of mu for a given particular of b, where mu square plus 1 can be achievable just because lambda square plus 1 is achievable. A good question, more of the challenge to explain your solution than to understand the solution.